technical brief will be on the technical underpinnings for ground vehicle mobility, critical mobility elements. He says, Bobby Hodges, Robert Hodges, who is Chief Technical Officer for NATC, is going to give us the brief. NATC was formed in 1957. Hank Hodges was the key lead there and started and it's a family-run business. Henry took over. I worked with Henry in 1981 with HML programs, some others, and now Bobby's been involved in the last 17 years working with it, and he's got a mechanical degree in engineering and is taking over the business and running in ATC. So he's going to give us an overview of proving grounds and their in ATC and how it's built, how it works, what some of the new efforts are in ground mobility, where it's going. The Marine Corps, U.S. Marine Corps is one of their key customers. They have a lot of private organizations that come to them for testing and evaluation. So they have a lot of background in new developments as far as testing, evaluation of vehicles. So without any further ado, I'm going to turn it over to Bobby from NATC. You have the floor now.
Awesome. Thank you, Dr. Mason, and thank you, Varsha, for setting this up, and all of you for calling in. And I see some familiar names out there. We got Dr. Oli Balling and Dr. Mike McCullough and Porf. I appreciate you guys calling in, and it's actually excellent that you have called in, because the briefing that I'm putting out there today, it's a little bit of a history and a story of how we got to where we are today. And those names that I just named off, you guys are the founders of influence of how critical mobility elements have been developed and the lessons learned over time. So the story that I'm going to tell today, I've heard many times from my dad, and but it's really not my story to tell, especially with some folks on the line here that lived it. And so definitely, as I go through these slides, I invite you guys to add those lessons learned and critical elements, because I think this briefing will be fun and educational, and really lay the groundwork for how we got to where we are today for evaluating ground vehicle systems. So just a quick introduction of myself. So as Dr. Mason alluded to, I'm the CTO out here at NATC, and I've been working here now for a little over 17 years. And excuse me, my background's a little bit of a Swiss Army knife. I've touched everything from ultralights up to heavy transport combat vehicles and everything in between. And as an engineer, my primary role was working Marine Corps and special projects, efforts in support of US SOCOM and various other things. But nowadays, I'm a little bit of an inch deep and a mile wide. At any given point, we NATC have about 40 to 50 different projects going on, everything from tire testing to robotics to winter testing, environmental, vehicle design, and everything in between. So we'll touch on that a little bit. And before we get into the technical, I'll give a little bit more background on NATC for those that haven't been here before, and who we are. So from NATC bottom line up front standpoint, who we are and what's our deal. So as Dr. Mason alluded to, we were founded in 1957, and I'll get into where our founding fathers came from and how the company was originated a little bit later. But we are a small business, HubZone certified, about 140 employees, and still family owned to this day. My sisters and I took the keys back in 2021, and we've been running the place from a day-to-day standpoint ever since. So I got to give a shout out to my sister, Kelly Hodges. She's the CEO president of NATC. I think she's on the line as well. So Kelly, please add anything as we go, as you see fit. But today, in terms of the services we provide, our name implies just testing, Nevada Automotive Test Center. But the reality is we're really concept to completion. It's everything from prototype development, requirement information, informing our customers of the realm of the possible, all the way through validation testing to confirm whether a OE meets government or industry requirements. And that kind of concept to completion is really what delineates us from many folks. There's not many entities that do the full spectrum. There's groups that focus on testing, there's groups that focus on design, but there's very few that cover the full gamut of ground vehicle development, and that is our niche. In terms of workload split, Marine Corps is our number one customer, but we're about 65-35 split in terms of military versus commercial, and the type of work that we do. And overall, the engineering expertise is key. Being a proving ground, yes, testing is important, and we have a bunch of tests going on, but every test is run by an engineer, which is a little bit different. Not many outfits approach it that way, and that engineering expertise with the heritage of testing pedigree is very important to us. We have two locations. The central location is where I'm at right now, Silver Springs, Nevada, but we also have our winter test facility up in West Yellowstone, Montana, pictured there on the right. And of our 140 employees, about 25% are veterans, and it's pretty important to us because of the type of work that we do. But overall, at the bottom there, a little bit of our catchphrase: we're caretakers of the lesson learned by those that came before us, postured to evolve based on rapidly changing industry capabilities and associated end user needs. And that's really important. Being a company that's been around since 1957, it's important for us to be caretakers of the history. And that's something that my dad has preached for many, many years. And that's why we're here today. And that's why the briefing is set up the way that it is to recap some of those historical lessons learned. So real quick, the services that we provide, what we do out here. I alluded to it a little bit on the bottom line up front, but really you can divvy it up into 4 different categories. And number one is test and evaluation, whether it's new design tests specifically for a certain scenario or an event that's unique to a user. For example, we had to develop a new test because the Marine Corps was having some issues in Australia. They were having ironwood going through floorboards on their M-razors, and it was hurting folks. So we had to design a custom-built test for that specific scenario. But then also valve air testing. So that's your standard, ASTM, SAE, ISO, TOP reference standard. And our role as the independent third party is valid. It's a BAE, Oshkosh, Michelin, whoever. We're the independent third party that can confirm to the government or whoever the prospective customer is that the claims of that OE are in fact validated for the requirement. And we've been doing that for many, many years. DOT&E, so developmental and operational testing. So something that's very important to us is having actual operators out here. And anytime we're running a test, it has to be operationally relevant. It has to tie to something that resonates with an end user. So we actually host end user events out here on a semi-frequent basis, but getting young Marines and SOCOM operators on site so that they can evaluate the vehicles, provide that feedback, and help us understand their concept of employment. So then we can recreate those scenarios out here for testing. Live fire survivability, so ballistics, underbody blast, the full spectrum there. Interop and environmental, very important on the government side. So compatibility between, air transport, rail transport, over the road, et cetera, et cetera. And then safety assessments. We actually write, safety assessment reports to help release vehicles for use by end users. And that's a key aspect of our business there. Then research and engineering. So I touched on it a little bit, but testing puts us in a pretty unique position because we've seen so much out there and been involved in these vehicle system level evaluations. we're in a unique position to help on S&T efforts. So requirements development and technology demonstrator builds. And, we're not in the business of ever mass producing anything. We're a small business, but it's important to us that the requirements bound the realm of the possible. So we can take a ground vehicle and design it from the ground up. And it really doesn't matter to us whether it's a Bridgestone tire or a Michelin tire or a Cummins engine or a Duramax engine. We truly can, utilize any component. It's really what's the right component for the application. And then we build this one-off concept vehicle that can help inform requirements. And then the government will take those requirements and then see what the OEs can provide and help move the goalpost a little bit. Then training and demonstrations, a smaller aspect of the business, but we do conduct quite a bit of training with some Marines. We had about 20, 30 Marines out here for a training event last week, learning how to drive various vehicles and stuff like that. But then also industry days and tech rodeos. So we have an annual tech rodeo that we do where we host about 400 people from industry and government reps. And overall, the goal of those tech rodeos is to bridge the gap, between technology that exists in the industry and a requirement and a need that the end user has, and then combining those to find solutions. And we've been doing those tech rodeos for a number of years. And then lastly, special projects. So urgent needs, whether it's accident reconstructions, mishap investigations, various things like that. And those are typically the projects that I get to do. So I get to dabble in engineering every once in a while. But overall, the goal for NATC is to be a one-stop shop for system and component level test and engineering. And then this is a new slide that we've come up fairly recently, but in terms of how we approach ground vehicle test and engineering, these are our pillars. And these are pretty important to me, and it's something that we've been chewing on for a while. But if any engineer at NATC comes into my office and asks, like, how am I supposed to approach this problem? And what are we trying to do out here? These are the 5 pillars that are dictating success at NATC. And if we're doing these 5 things, then that ensures that we're aligned and we're providing the service that we want to be providing as a company. So I'll walk through them a little bit here. It's being curious, right? And understanding the why. Why are we running a double lane change test? Why are we running a tractive effort test? And how is that relevant to the end user? And what does that mean for employments? It's taking things a little bit further so that we can better understand problem statements, objectives, and align with our customers. So it's not just taking directions saying, yep, I'm rocking and rolling. It's more, why am I doing this? Asking questions as we go so that we can be sure that we're aligned. Being comprehensive. You have to be, excuse me, adhering to industry standards. We're out here in the middle of nowhere, Nevada, but we have to be sure that we're looking at things and staying on the cutting edge, being involved in the community, such as ISTVS, NATO conferences. We have to be comprehensive, and we have to be working with our industry partners to ensure that we're aligned and maintaining that high quality. Collaborative, whether it's gov to gov to industry, everybody has different pieces of the puzzle, and it takes someone combining all of them so that we can understand the big picture and put it all together so that we're solving the big problem. And in order to do that, you have to be collaborative. So it's not operating on an island. And that's tough as an engineer. You gotta come out from the weeds every once in a while and see what we're doing and why we're doing it. Being pioneering, it's thinking outside the box, pushing the envelope at the edge, immersing into the data, looking at creative ways to insert tech, and looking at what's going on with Tesla and what's going on with Nikola and all these companies, and how can that technology be leveraged in these other applications to bridge that gap. And you guys have all heard it, there's recent mandates and pushes for leveraging COTS. Everybody's talking about leverage COTS. So what can we do to look at where the industry is at and take that technology, modify it so it's applicable for these different end users? And then lastly, it's being passionate, man. You got to be passionate. And, it's taking on our customers' problems as our own. You got to have real-time solutions, adapt as you learn. And it's really, really important for us to be passionate about what we're doing. Otherwise, why would we do it? So anyways, that's how we try to approach things out here at NATC. And then lastly, on NATC, just a quick overview of some of the resources. Dr. Mason mentioned there's some folks on the line that are interested in maybe building some proving grounds in some foreign countries. And this is kind of what that looks like. There's a lot of resources required to operate vehicles in this severe environment. You have to have the shop space and the welding equipment and the mills and the skilled staff to do it, and having that staff on site instead of contracting it out is really important because, it's a unique service running these developmental testing vehicles through the gamut of tests. They're going to break, and you got to have the facility and the equipment to keep them moving, especially in today's atmospherics of schedule being king. You got to move fast. So having the adequate resources and tools at the disposal of the engineering staff is really important. And then on the data side, instrumentation, overall, we got thousands of sensors. It's everything from accelerometers to displacement transducers, thermocouples, different acquisition units, and all the associated tools for processing that data and correlating it to virtual models. So that's NATC in about a little over 10 minutes. And so now let's get into the juice here. And overall, the next hour or so, I kind of want to kill two birds with one stone. And we're going to explore the evolution of critical mobility elements in ground vehicles over time, and then how we, what's the ability to actually simulate them in the virtual environment. And then simultaneously talk about the company evolution over the decades. And talking with Dr. Mason, we wanted to tell that story with you guys because it's a pretty fascinating one. And there's a very unique butterfly effect of this whole thing that is interesting. So getting into it, looking at the technical underpinnings of ground vehicles, mobility is a critical aspect, but we don't have enough time to get into all of them. There's reliability, there's underbody blast, survivability, steering and handling, environmental, and for the vehicle designers on the phone, everything's tradable, right? So if I want to improve my mobility or my payload or my performance, I'm going to have to give something else up. And us as a community, ISTVS community, obviously mobility is critical for us. But it's reminding folks of that, okay, if I want to add this counter UAS system, or I want to add this weapon system, or I want to improve my steering and handling performance, or my payload capacity, that's going to impact mobility. And it's ensuring that our customers, our mutual customers, are informed on that trade space so they know what they're potentially sacrificing by improving these other metrics. And today we're going to focus on mobility. I think everybody on the phone is big mobility proponents, so I'm sure I'll be preaching to the choir a little bit, but it's definitely something we'll have to keep pushing as a community. The future fleet demand signals, as we've all heard when you go to the trade shows, whether it's GVSETS or Modern Day Marine or Eurosatori or any of the big conferences, on the US side, we're all looking at replacements for a wide range of its legacy fleet. And the demand signal that we're hearing is, okay, we need to meet current ground vehicle mobility capabilities, but we also want to look at advanced propulsion. We want to extend our range. We want to have better onboard power generation, and we need to export power in the field, and we need to be safer, smaller and lighter. I've heard that constantly over the past 6 months or year. in order to answer the question of future fleet mobility expectations, we got to look at what drove the current fleet to be what it is today, right? We have a pretty good fleet from a mobility standpoint, and we've learned a lot. But as we look to incorporate hybrid electrics or onboard power or any of these other things, what are the current fleet's capabilities and what lessons were learned that drove that current fleet to be what it is today? And that's exactly what we're going to talk about in today's brief. The butterfly effect goes all the way back to World War II. And, looking at World War II mobility challenges, that was, for the history buffs on the phone, that was the problem, right? The U.S. had a lot of challenges in World War II from a mobility standpoint. Some of these pictures demonstrate that well, coming ashore in Normandy and across the Eastern European plains and even in Africa. There's a lot of challenges. And the Willys Jeep, the Willys Jeep wasn't developed prior to World War II. It was developed rapidly during World War II because we didn't have a material solution. We needed something. So the mobility challenges that our armed forces had during World War II really set the stage for many things, including NATC being founded. And I'll get into that a little bit here in these next couple slides. So coming out of World War II, there was a task given to the U.S. Army Corps of Engineers. And because of those struggles that our armed forces had, the task that was given was better understanding mobility, terrain mechanics, studying worldwide terrain, and all these different aspects, right? And the study, really the end state target of the study was trying to find an ideal location for test and evaluation for mobility, right? And the study took many years. As my dad tells the story, it took about 10 years. And the study was completed in 1954, and it identified that Nevada was an ideal location for this exact need because of the soil diversity that exists in Nevada. Geomorphologically, that's the term my dad uses as he describes it, Nevada is an extremely diverse state. And it comes from the glaciation of the Great Basin here. As the glaciers receded, it turned into a melting pot of terrain, is the best way I can describe it. So in terms of all your fines and your courses and the loam and everything, it's a very diverse state. And they found that 85% of the soil types that exist in the world are located within about 150-mile radius of Fallon, Nevada. And Fallon, Nevada was identified as that location that would be ideal for a test and evaluation center. So enter a young Henry Clay Hodges Sr., pictured on the top left. That's my grandpa, as well as my grandma, Martha Rogers, pictured there on the top left as well. So my grandpa served in the 10th Mountain Division during World War II, and he was responsible for the mountain pack mules, specifically in northern Italy. So you can imagine mountain pack mules in northern Italy, mountainous terrain. You got to have some grit to operate in that environment, and being mobility inclined, you can see how that seed was planted, if you will. Living that life and experiencing the challenges of getting equipment and howitzers and everything through that terrain, mobility was king for him. And in parallel to that, my grandma, so she was a tough cookie, man. She was a Colonel Select, one of the first 5 WACs deployed overseas. She served under both General Patton and General Eisenhower's staff directly. And that picture with her face on it, with the little yellow circle around it, that's actually after she was torpedoed, and she was in a transport ship, and that was in a French newspaper as the U.S. forces were rescued coming ashore. So she had quite the experience. But similarly, you can imagine serving directly for General Patton and General Eisenhower. She got exposed to the limitations, the mobility and the route planning and the strategy and everything that they had to do to be successful during World War II. She was right there as a staffer. So they met, and this great story that we don't have time for today. But the end state is my grandpa actually worked at Aberdeen Proving Grounds for a number of years. So he was in the test and evaluation community, and he got his hands on this Army Corps of Engineers report, and he was a big believer in it. He said, that's key. We got to match dirt for dirt, dirt for dirt, dirt for dirt. He said that so many times growing up. I heard him say it. So he really bet the farm. He moved the family out to Nevada. He's a stern believer in it, and grabbed the Pontiac station wagon, moved cross country, bought the ranch, and away we went. And the core aspects of the business from day one were soft soil mobility, and that was the focus that he had as the company owner for many, many years. So this next video shows the facility, and it's a little bit of a drone flyover, kind of cool recent video we took. But overall, the facility that he purchased was about 6,600 acres is the main ranch, and our operating area gets out to about 1,200 square miles through our use permits with Bureau of Land Management. So we're very rural out here, very secluded. And the surrounding terrain around us is all, federally owned land. But it's a network of test courses. We have a little over 1,000 miles of measured test courses on site. So it's not just some random road in the middle of nowhere, Nevada, right? Any testing that we have to do out here, it has to be validated to something. It has to be correlated, and it has to tie to something that's relevant for end users. So you can see these videos of some of these vehicles going through the mud, and that's our Southeast Asia area. The soil type is very common that you would see in rice paddies and things like that. But then also the river running through the property is critical for us. Yes, we're in the middle of the desert, but maintaining the mud and the corrosive environment and all those things, we have to leverage some of these, alkali flats and various other things to represent those worldwide conditions. So with some of you guys on the phone, this will resonate very well with you. Now, fast forward to 1970, the original Army mobility testing. So the NATO Reference Mobility Model, NRMM. So for those that aren't familiar with that tool, that is a simulation tool, and it was developed originally back in the 70s by Army, TARDEC and ERDIC in collaboration, and it was cutting edge. Nothing like it existed at the time, and the objective for that tool was to help provide an empirical data set that could provide predictive mobility and inform the NATO fleet on go, no go, speed made good, all kinds of different things. So a very powerful tool, and something that was invested and tested for a number of years. A lot of that testing was done out at NATC, and NATC was selected as a location for a lot of that full vehicle mobility testing to develop the original NRMM. Now, NRMM, that's the methodology that's been used as the criteria for predicting vehicle mobility for about 40 years now, and recently it's been updated, and we'll talk about that a little bit. But overall, it's a two-dimensional simulation environment, and the accuracy of the tire representation is really the limiting factor of it. Back in the 70s, the vehicle tech, it's pretty basic stuff, right? Bias ply tires were very common, and solid axle suspension. So because the vehicles really were, a little limited from a mobility standpoint, you could use a two-dimensional simulation environment to get some, decent representation. But over time, we've learned that tool needed to get updated and delineate between radial and bias ply constructions, and overall the fidelity of it for deformable soils needed to be improved. But overall, in the 70s, this was a very important effort, and that set the stage for so many things down the road. And a lot of folks on the phone call have lived a life around that butterfly effect that I'll keep talking to. So now, let's see, 1979, a key milestone here terrain profiling. So this was one of the original efforts for establishing criteria for validating test course profile and roughnesses to be representative of mission profile worldwide conditions. So in the late 70s, kind of what's going on, right? The M1 is coming online, the Bradley's coming online. So those test efforts are sucking up all the resources, right? And the government proving grounds, Aberdeen and Yuma, are saturated, right? And they got a lot going on. So they needed somewhere else to do overflow testing, and your other assets like your M113s, your tactical wheeled vehicles, your trailers, things that were a little less high profile, but also still significant. So NATC, we partnered with the Army and TACOM to work this problem and be established as an overflow test site. But the critical milestone, and the reason why I included in this briefing, is this effort helped dictate the original quality control for test course profiling between all the different proving grounds. So in order to ensure that we weren't introducing variables to test results, we had to be sure that if you test at NATC, you test at Aberdeen, you test at Yuma, the test course profiles wouldn't introduce a variable or an anomaly for failures. So we had to be sure it was matching those profiles. Now that's important because as soon as we establish that criteria, then that helps inform terrain profiling outside of proving grounds, right? Well, if this is what the proving grounds are doing to ensure that their profiles are set, how do we measure profiles in worldwide OCONUS or CONUS conditions? And this was one of those first efforts that nowadays a lot of folks on the phone are living that, of LiDAR and photogrammetry and down to 1 centimeter resolution on terrain roughness. And is that adequate? This was the effort that started a lot of that back in the late 70s. So now into the late 80s here, a little bit back on NATC and kind of an interesting story. So in 1987, NATC was actually on the verge of bankruptcy. We were down to about 20 employees. And the biggest reason why is that the testing and the mobility testing that we were doing pretty much dried up. And a lot of the testing services for tire manufacturers, that all went in-house as tire manufacturers went to the force moment dyno machines. The need for a lot of this real world testing kind of went away. So my dad took over the business at that time, and he was at a true crossroads, man. He had to gamble. He had the ultimate fork in the road of adapt or die. And do I stay with the company? Do I invest and change? Or do we sell it and move on? And he had a job offer to go work at Boeing as well as Armstrong Tire at the time. And my mom just had my daughter, or my sister, and she went to McDonald's with my dad, and they had the discussion over a Big Mac. And basically decided, nope, we're going to stay at NATC. And my dad's vision was to pivot away from just traditional proving ground services to more engineering focused efforts. So instrumentation, digital engineering, modeling and simulation, interop capability, and all these things that are showing in this video, that stemmed from his vision to adapt away from just a traditional proving ground to more of that one-stop shop engineering service. He'll tell you stories about taking a second mortgage out on his house to pay for the first Honeywell data acquisition systems and various other things. Now, the reason why I included this slide in this briefing is this decision postured NATC to then help as part of predictive mobility and engineering services and all those things that we've talked about a little bit. And if my dad didn't make this decision, then I don't think I would be on the phone with you guys today. We'd be doing something else, right? We wouldn't be part of the community. So, truly a wild decision for our family and the company. And, I put it to him, man. It's takes a lot of grit to make a decision like that. So now fast forward to 1991, and in 1991, the Marine Corps, they were at a little bit of a crossroad, as did the Army, and they had to make a decision of, do we go with the Army to procure the FMTV pictured on the top right, or do we go out on our own and buy our own vehicle? And that was a big decision, difficult decision. That decision that they made was based off of mobility. And I'm going to tell that story here in these next couple slides, but the reason why the Marine Corps ended up going with the MTVR instead of the FMTV ties to mobility requirements that the Marine Corps had and the ability to simulate them. And it's really pretty interesting. So we'll tell that story here. The mission profile for the Marine Corps was developed to ensure worldwide deployment. They're austere environment, right on the front lines type of service. So the task that was given to NATC at the time was, okay, we need to understand what is our requirement for mobility for our 5-ton replacement. And, what does that look like so that we can decide if we're going to go with the FMTV or we need something different. So this was a study, and it was actually done in collaboration. It was NATC, ERDIC, CREL, various other DoD agencies. It took a village to pull this off because it was a big effort. And the end state was, if you want to ensure worldwide deployment, these are the 5 operating areas that you need to check the box against. I.e., if I can operate in these 5 operating areas, then I'm good for worldwide conditions. So there's a big briefing that goes into this, and my dad's briefed it many, many times. But overall, this is the punchline, is after that effort of understanding soils and leveraging ERDIC and working together and collaborating on this whole thing, this was the end state. And it's pretty interesting. You look at Costa Rica, the Philippines, Southwest Asia, Norway, and Korea, as our kind of worst cases, it kind of makes sense. You got your wet, hot Costa Rica, the coastal plains up to the mountains, the Philippines, that triple canopy jungle, Southwest Asia, the very arid and aggressive cross-country terrain. Norway, that's a freeze thaw, the shoulder seasons, very challenging from a mobility standpoint. And then Korea as well. So this was a great point of departure for establishing. We knew that these were the worst cases. Then you deep dive, right? You hone in, you better understand those terrain areas, and then you can define it in engineering terms to help inform ground vehicle design and requirements. So we'll just walk through that step by step. This is what that IPT did as a group, and Dr. Mason and and Dr. Shoup and various folks that are on this phone call and are still part of the ISTVS community. They were part of this effort and really the forefathers of mission profile development. But it's a pretty simple process, but it's overall very, difficult from an engineering standpoint. But step one, you got to find the route. What are the end users going to want to do with their equipment, and how are they going to want to operate in this area? So relying on end user feedback for defining that route is very critical for your point of departure. Then once you have that end user feedback, you quantify the attributes of the terrain. You take that route and you define it in engineering terms. What's the soil type? What's the terrain type? What kind of foliage do I have? What kind of frequency do I have for gap crossings, et cetera, et cetera? And then once you have all those attributes defined in engineering terms, now you have a homologated composite mission scenario roughness calculation. And that is the golden ticket for vehicle design and ensuring that test and evaluation in either the virtual or the physical environment is representative so that when the vehicles get deployed, they're off and running. So this exercise is critical for ground vehicle development. So this was one of the example routes. This was a Costa Rica notional mission back in the early 90s. And, overall, these were just some options. There were different concepts, airfield seizures, and, worst case, we had to do something. What would it look like? Entry positions, coming ashore, working with McCITIC to define those typical mission sets, right? So some nice pictures of what that exercise looks like. Then you go in and you quantify those attributes. And in the 90s, there wasn't a lot of data available. Nowadays you got so many between the worldwide soil databases and USDA and NGA and all the different options. But back in the 90s, a lot of that didn't exist. So some of these measurements were actually done in country, and Marine Corps didn't have any money at the time, so they just did what they could. They actually partnered with Chiquita Banana of all companies, because Chiquita Banana is running down there. They said, hey, can you guys just, take some measurements as you're down there, help us out. And those are just some of the crazy stories, and that's how it was done. But it all worked out. And overall, this was an example route where, the soil types were quantified, and, the terrain types were measured, and foliage was characterized, and all this data was developed to ensure that we're mimicking what they're actually going to experience if they deploy in that environment. So then, now that we have all that data, it opens up the gateway for quantifying terrain roughness, and whether that's in-country measurements with profilometers, whether that's using nowadays, there's options with laser scanning, there's options with drone flyovers, there's all kinds of things in the works. But tried and true is your ASTM Type 2 profilers, and one of those are pictured in the top right. But whether that's shipping the vehicle out there, or there's various ways to do it, but you get these nice ribbon plots of elevation versus distance, and now you're off and running, man. You have a true blue profile of the operating environment, and we can ensure and recreate those environments on a proving ground or in a virtual environment. And it's a very elegant process that this IPT came up with back in the 90s. So the end state here in 1994 was the severe mission profile was defined. And this is a great little table. Unfortunately, we don't have enough time to go through the whole thing and what WNS is and what RMS is. But the bottom line here is that this table summarizes day in the life of a military vehicle, whether it's any military vehicle that exists. They're going to use some version of this table, and they're going to have different proportions of percentages for how much time am I spending on high quality paved, and how much time am I spending on trails or cross country. Now, trails, cross country, high quality paved, those are interesting terms, but we need something mathematical to ensure that we know what that means. What is a trail? What is a cross-country course? And that is what the WNS and the RMS values do, is it allows us to actually create profiles that match that roughness level. Then also tying that percent day in the life to speed expectations. What is the end user going to want to do from a speed over terrain? And this table is, it's the holy writ, man. This is what drives so much from a vehicle design, from a testing standpoint, from everything. And it came from an effort in the 90s for the Marine Corps. And now this table gets used in so many areas, OEs, we have BAE on the phone, and we have Oshkosh on the phone, and folks from those entities. This is key for ensuring that we design vehicles successfully for deployments. Now, one of the sidebar takeaways from this was that the mission profile, getting back to the whole 5-ton decision thing, what's the Marine Corps going to do? Are they going to go with the Army, or are they going to go out on their own? The end state of this study that was done as a community was that the Marine Corps' worldwide mission profile was 2.5 times more severe than the Eurocentric mission profile that the FMTV was originally designed for. So you can see that plot on the left. The proportions are way different, in terms of percent operation for primary, secondary trails cross country, but also the level of roughness and expected day in the life severity is also significantly different between the two. So if you want to be successful for worldwide deployment in these austere environments, it's that orange and red plot, that's a very severe day in the life. Versus if you're just operating in a Eurocentric type terrain, it's not quite as severe. So this was the primary defense for why the Marine Corps pursued their program of record as compared to the FMTV, and that led to everything, right? Reliability, life cycle cost, mobility, energy efficiency, and all those different things came from this study that was done by this community. This table that I briefed is still used today, and each vehicle that's out there has different proportions, different speeds, and ATEC, that's the Army testing agency, they updated their standards to require WNS and RMS methodologies for measuring terrain roughness in 2017, and this table continues to get used today in various efforts. So still in 1994, now think about it, right? We just established, okay, we need something different than the FMTV. And what is that, right? What level of vehicle capability is necessary to meet that day in the life severe environment? Material solution, we got to come up with something. And, looking at the 5-ton evolution to the MTVR today, some of those highlights are listed below, and this was actually done through a tech demo effort, again, in collaboration, NATC, Marine Corps, various other DoD agencies worked together on this. And that tech demo helped bridge the gap between the low mobility 5-ton Vietnam era vehicle to the MTVR, which is the gold standard of mobility today. And that mission profile that I talked about is why this vehicle ended up being the way that it is. It's got 16 inches of wheel travel. It's got central tire inflation systems, tractive effort ability of 0.4 on all surfaces. And for the tractive effort folks on the phone, that's not easy to achieve. 0.4 lateral G acceleration. So stability, that was a big concern, right? If I have this big mobile vehicle with 16 inches of wheel travel, independent suspension, am I going to be safe? And that was a big effort to try to figure out how to do that. So many of these material solutions, these were cutting edge in the 90s, right? You look at suspension manufacturers in the United States in the 90s, no one really was doing this, right? So the suspension that was required to meet the Marine Corps requirements, it actually came from a company called Tatra, and some of you might be familiar with that. They're in the Czech Republic. But that type of suspension was really kind of unheard of in the United States industrial base. Nowadays, there's so many companies that do that, right? There's Timony, there's Meritor, there's Oshkosh, everybody's got their, various other folks that are working this class of vehicle independent suspension. But in the 90s, it didn't exist. So, we had to, as a community, again, be a little creative for how we came up with this material solution. Now, tying back to ISTVS and NRMM, we have this vehicle, right? And we have this tech demo, we have this MTVR class vehicle. The community was interested in, okay, this vehicle that was just designed for the Marine Corps is quite a bit different than all the vehicles that were used for developing NRMM back in the 70s. How does NRMM do for predicting mobility with these future fleet capability, right? Humvee's another good example, and SUSVs, and the 5-ton as well had some upgrades at that point. So this was an ISTVS effort that was done in the 90s, And the effort was a blind prediction. Essentially, ISTVS took it on to determine whether the current and future fleet could still leverage NRMM for predictive mobility, knowing that the future fleet and these new vehicles had much different vehicle design characteristics. Overall, there's some tracked vehicles, some wheeled vehicles, and the effort was, leveraging go, no go, speed made good, and all the different outputs that NRMM does. But it was a blind prediction, right? Run the test, see what the vehicle can do, run the test in the virtual environment, see what the output is, and compare the two. Let me back up one. And this was the end state. So again, don't have enough time to go through all these, but predicted versus actual, you can see that there's a very big difference, right? And the speed made good over mud, speed made good over cross country, different mission sets. NRMM at the time, it under predicted and over predicted performance by quite a bit. And the end state here is that ISTVS set the stage to get updated and replaced in the 90s. And the community was, invigorated. And as my dad tells the story, we're all on the same page that, hey, this needs to be done. The problem was there was no funding available for this effort. So it took a long time, and some of the folks on the phone actually were leads on that effort. But in 2014, a NATO effort to update the methodology was initiated, and that's called Next Generation NRMM. And over 100 elements within NRMM were identified as needing to be updated or replaced to ensure that this future fleet and the capabilities of this future fleet can be represented in the virtual environment, and that NATO tool can be used again by all of our NATO partner countries. So the existing NRMM continued as the only approved mobility prediction tool for the Army up until about 2022. But then due to the efforts of a lot of folks on the phone here, that was rolled out in 2022. And now we have a new StanRec to use for better mobility predictions. And it all started with an event in the mid 90s out in the middle, and it's fascinating looking at this whole history and how this all came to be. But the outstanding question of this is, okay, what are the operationally relevant critical mobility elements that need to be tested in both the real world and virtual environments to ensure worldwide mobility? Getting back to the point of this brief, critical mobility elements, what are they? So I'm going to show some videos. Unfortunately, these videos are available to show to this audience and be out on YouTube. So this is a good go, no go difference between two vehicles, vehicle on the left versus vehicle on the right. Overall, vehicle one's a go, vehicle two is a no go. Why, right? It's easy for us to show a video, and you can find videos online of all kinds of stuff of, folks getting stuck and all that good stuff. The question is why, and under what engineering conditions did this happen? The reason why vehicle one is able to make it through this go is simply it's a big tractive effort, event. It's in fine-grained soils at various moisture contents, and this delineation between these two vehicles is an engineering aspect. You can quantify it. Vehicle one has 35% more tractive ability than vehicle two, and overall wheel travel, torque management, traction to mimic vehicle one performance, that's what you need to get this level of capability. So critical mobility element number one, if you will, is tractive ability. Here's another one. So a lot of folks on the phone are probably familiar with vehicle cone index and cone penetrometers and that type of measurement. But you can see vehicle one gets stuck almost immediately, and vehicle two will progress for a good amount of time. Why, right? And vehicle two has quite a bit better vehicle cone index, that's flotation, soil trafficability, et cetera, than vehicle one. And one of the biggest reasons why is just simply tire size, right? 16R20s versus 395s. and it's torque distribution, it's ground contact pressure, ground clearance. Those are all design features needed to ensure my future fleet have adequate mobility. So call it a critical mobility element. Number 2 is vehicle cone index, in no particular order. Here's another one. So this is over the beach. So this is a critical sand grade climb. This isn't the actual test area where we would formally run this test. It's more for demos and stuff. But you can see vehicle 1's going to be a no-go. It's in a little bit of a traction hop, a little bit of slip. And now we have vehicle 2 being able to go. So again, why, right? And overall, it's weight distribution, it's weight transfer, suspension. Overall, it's critical dry sand slope performance is the metric, but weight transfer characteristics and traction management is critical for getting that level of mobility. Then here's another one. So this is your speed over mission profile. So we have vehicle 1 or A, if you will, and then vehicle 2, B, if you will. And you can see the ride quality, the shock and vibration going into the occupants are significantly different. And that is going to limit speed, and overall, this is what we call absorbed power, weighted acceleration, but it's ride quality, right? Both those vehicles are going at the same speed in those videos, and inherently vehicle 1 or A is going to be able to be faster. It's going to have a better time to complete mission. It's going to be better on your equipment, better reliability, all kinds of different things. So this is all, it's wheel travel, it's suspension control, it's again, weight distribution, absorbed power, weighted acceleration. That's a critical mobility element, number 4, if you will. So, okay, we have some critical mobility elements. That's great. How can we simulate those? And in the 90s, what kind of simulation tools existed to have that level of fidelity, right? We've just identified, okay, we NRMM, we want to update it, it needs to be better. Our future fleet's getting better. How do we do it? And are there tools available to do it? So in the 90s, there were, as a lot of folks on this phone know, but in terms of the fidelity of those models, they're maybe not quite there. And you can see just from these videos, there's some good lessons to be learned, and they're a good tool in the toolbox. But in terms of, getting into soft soil, deformable soils, there's some limitations there. And, we needed some more time. Industry needed some time to develop the tools to get to the point where we need for good virtual digital engineering. So what do those tools need, right? You got to be able to understand the vehicle capability, and you got to have a virtual tool that can ensure that we're mimicking ground contact pressure, gross motion, adjustable features, right? A lot of modern vehicles have so many different adjustable features in them. The virtual tools that are being used need to have that capability. We need a vehicle model that is validated to operationally relevant conditions, right? Easy to say, hard to do. You got to understand the human aspect, right? Do you have a novice operator? Do you have an expert operator? Driver fatigue, right? If your vehicle go is dictated by your operator being highly skilled and fresh, then that's risk, right? Because any operator is going to be, there's going to be fatigue, there's going to be human factors. So risk tolerance for braking, right? How close to end limit do I need to operate to meet the requirement? Or do I have gray area? Do I have reserve capability in the vehicle? And various other things there. So we need our virtual tool to be able to adjust route and mobility based on risk assessment from a human factors standpoint. You got to have that level of capability in the virtual tool. And then finally on the terrain side, and I'm again going to be preaching to the choir to a lot of folks on the phone, you got to have data on roughness and slopes, soil composition, moisture content, vegetation, overmatch for trees and all kinds of different things. Terrain composition metrics is critical, for many, many reasons. So we need real-time terrain data with layers beyond just terrain roughness in order to ensure that we're modeling this mobility and these critical mobility factors accurately. So key takeaway here, NRMM replacement, you got to consider the vehicle operator and terrain as a system to ensure that we're providing good utility. So now fast forward to about 2000, and the Marine Corps, they leveraged some simulation tools. They were one of the first entities to look at a simulation-based acquisition for buying a future fleet vehicle. So from 1994 to the year 2000, the tools got better, and softwares were developed, and everything kept trudging along. So we got to the point where the industry, in collaboration with Office of Naval Research and some folks over there, they leveraged simulation to down select vehicles for acquisitions. And they compared different designs, and they compared different OEs, and compared all these different things. They did it in the virtual environment. So then they did a down select to, I think it was 2 vendors at the time, to proceed to physical testing. It was all template based, right? So they developed templates for scenarios, templates for their vehicles that then these OEs could use and leverage for vehicle development. And the users can go in there, modify, the templates to match their actual vehicle designs. And it was all common inputs, common standardized road roughness courses and various other things, and allowed for the community to make performance comparisons in the virtual environment between all kinds of different options and vehicle designs. And this next slide shows that a little bit here. This is a double lane change maneuver. A lot of folks on the phone are familiar with it. Very standard stability test. And this is one of the tests that was used to validate the virtual models and the templates that were provided to the OEs in the virtual environment. So a good demonstration that the tools continued to improve over years and years, and the Marine Corps and ISTVS and ONR were all integral in that. So 2005, things are moving along. Now we have, again, future fleet. We're going from the Humvee to the JLTV. So now we have much more capability from a mobility standpoint, ride height adjustable, different things from a suspension standpoint, semi-active suspension instead of a passive suspension. That's key. So how do I include a semi-active or active suspension in the virtual environment? In the mid 2000s, that was a problem. How do we do that, right? And nowadays it's common practice, but that was critical. So looking at these material evolutions and how industry is evolving its tech, we got to be sure again that our virtual tools and our tools for test and engineering are keeping up with these capabilities of these future vehicles. So in 2010, we transitioned, and the tools were there, right? Deformable soil modeling was right at the edge, and honestly, what was leveraged here was underbody blasts. Think about what's going on in the 2010 timeframe. There's a lot of IED problems for the U.S. military. So in order to model IED blasts, they had to really invest in deformable soils and that type of engagement underneath the vehicle. And a lot of lessons were learned that actually translated over to deformable soils for trafficability, right? And it's terra mechanics. And, the blast impulse, obviously is significantly different than a tire going over that soil, but how the soil particles interact with each other and, that deterministic approach is, it's all part of this whole effort. And in 2010, that deformable soil modeling advancements really came on, and those efforts continue today. Deformable soil is very tough, as you guys know, especially muskeg and bogs and stuff like that. But the tools are getting better and better, and the fidelity is getting better and better. And in 2010, those efforts really set the stage for the next evolution. So now 2019, almost up to present day. the community as a whole, due to the efforts of ERDIC and ISTVS and NATC, we played a supporting role as part of that. And, a lot of folks on the phone, international community, predictive mobility and the gateway to do that has really been opened up. And next generation NRMM really drove it. And, in parallel to that, NATC, we've been working with the DoD for a little over 6 years to try to figure this whole thing out. But it's really characterizing the capabilities of tracked and wheeled vehicles in both the physical and virtual environment, with the end state of a software that predicts mobility over any terrain conditions. And there's been so many NATO S&T efforts, and everybody's working this. There's ERDIC has a lot of excellent projects, meteorological and hydrology and understanding the moisture contents of soils. There's so many things going on in the community relative to predictive mobility. But it really kind of boiled up in about 2019. And bottom line here is that the simulation tools exist. There's physics-based model developments. There's ways to validate models against these critical mobility elements that we've talked about, terrain analysis and merging these layers, the physical testing. The tools have all gotten to the point where the floodgates have opened, and the realm of the possible really is there for the cutting edge of predicting mobility. And this is really that matrix. And I definitely want to give credit, the folks that were on the NATO committee to put this together. But these are those critical mobility elements. These are the test events for validating that digital twin. And it's so critical, right? You talk to all the different OEs, and all the different OEs run different pages of what is a validated model and what does that look like, right? Excuse me. And, these test events set that stage. So the community as a whole can all be on the same page of what is necessary for validating a digital twin and leveraging that for predictive mobility and testing. So a lot of basics here, some basic straight line accels, some good steering and handling dynamics, but a lot of the metrics we talked about: ride quality, shock quality, off-road trafficability, that's your VCI and your tractive effort, grade climbing, we talked about that a little bit, and then mobility map generation at the end. So most of these critical tests they're already commonly run, right? These are standard tests that are done. Now the tools exist so we can take that test data and that instrumentation data, tie it back to the digital model, and have a validated digital twin. And this is the end state. And you look at the 50 years, I briefed that in about an hour. There's so much more, and we barely scraped the surface, but it's a fascinating sequence of events that everything just kind of ties together and set the stage for where we're at. And it makes me wonder what's next, and where are we gonna push next. So overall, today's critical mobility elements and metrics, they're listed out here. And I've talked about a couple of them. We deep dived a little bit on a couple of them. A lot of you on the phone are familiar with these, but this is the hit list. And when you're developing vehicles, when you're testing vehicles, when you're working in the virtual environment, and you want to understand mobility, these are the metrics that will get you there. And a little bit of a cross deck. You can see most of these metrics are commonly found in purchase descriptions and P specs and things like that. But a lot of them are also now found in NATO StanRec 4813, which is the next generation NRMM reference. And really what these metrics do is, if you evaluate vehicles against them, you can delineate different tires, different suspensions, different powertrains, and what's the right tire for my vehicle. Is it a 16R20 or a 395, right? That's a big debate within the Marine Corps these days. So these metrics will help answer that question, and the expected level of performance within these metrics will drive OEs to pick an independent suspension or a walking beam suspension or a series hybrid or a parallel hybrid. they're so critical. They drive everything. So, any government reps on the phone and watching this on YouTube, you be warned, as you put these specs together, you're going to drive a lot of decisions by OEs. And, it's critical to know what you're trading. You put these metrics in your P specs. So where's the future going? And, it's optimal travel path and route planning and threat analysis and go, no-go zones and driver training simulators, all kinds of different things, virtual proving grounds, right? So by having these mission profiles developed, the roughness values developed, it allows you to take that real world terrain, recreate it in the virtual environment. That video on the top right, that's a drone flyover of one of our test courses. I think that's LiDAR data, I think. Might be 3 centimeter, but either way, helps you take that terrain, create the model, put it in the virtual environment, and allow OEs to develop their vehicles over the same exact test courses that they're going to be tested on for validation in the future. So that concludes the briefing. I went through that decently fast, just being respectful of everybody's time. And I think I see a couple folks that are calling in, and it's about dinner time, bedtime over there, Mr. Dr. Balling over there. But really appreciate you guys calling in, and thank you for the honor really to participate in this. ISTVS has been at the forefront for so many years, as we briefed here today. And, George Mason and the group that helps put these on and sustain it. It's so critical. Like I talked about, we're all seeing it. There's a lot of changes in the DoD and priority shifts and the funding cuts, and there's a little bit of shiny object, if you will, of, okay, we need to focus on drones and we need to focus on hybrid electrics and we need to do all these things. But at the end of the day, you still got to get the equipment from point A to point B. And us as a community, mobility community, ISTVS, that will always be important. And, folks like Dr. Sally Shoup, who focused on winter mobility, and Dr. George Mason and Dr. McCullough, and so many folks that have vested their life in putting mobility at the forefront. Us as a community, we need to continue pushing that. So best wishes to you all, and hope you guys have a great fall ahead of you. And I'll turn it back over to George for any questions and further discussion. So thank you.
So we got thank you very much. Thank you very much, Bobby. I had a couple of questions. I'll mention, if somebody wants to ask a question themselves in person, just let us know, and we'll make sure it happens. But I guess my first question was, have you been involved in Talisman Sabre over in Australia by any chance? That's kind of off the wall. That's a Marine Corps exercise along the coast there.
I have not personally been involved in any of those exercises. Typically, we get requests after. So when those events occur, they do their thing, and then we hear about the good, the bad, the ugly after. So yeah,
Okay.
Unfortunately, okay. I didn't get to go.
Well, when I see the regions of interest, that's I guess that matches up to Costa Rica, someplace like that. But it does match up the Pacific area coastlines. There are some support elements that go there occasionally that map it out before they hit the ground running. What features for mobility have you seen as far as cameras, LiDAR, radar units mounted on vehicle systems, maybe to augment mobility? I know y'all have Tesla right around the corner from you, and it's amazing the new things they're mounting on vehicles. Are y'all testing any of that?
Yeah, absolutely. That's a great question. So there's been many pushes for that, of whether it's leader follower, waypoint control, teleoperation on off-road vehicles. And bottom line, that we've seen a struggle with commercial approaches to autonomy being able to be leveraged in off-road environments. It's so different, and the controls for those vehicles and the inputs into the LiDAR, radar, photogrammetry are so different. Taking a kit that's equipped on any of those over-the-road trucks and trying to develop it for the severe environment of the Marine Corps, there's been attempts at that, and I'll just say they've been challenging for sure. And I would say there's more work to be done. There's a lot of limitations associated with the tech available on ground vehicles for making decisions on the fly. And to your point, George, route planning, there's a lot of efforts there. Like DARPA had their Racer X program that was very impressive, and they did a lot of tuning for route planning and using some of that photogrammetry technology. So I'd say there's more work to be done, but the solution has not been provided as of yet from our standpoint.
Yeah, I would think even cameras on some of those vehicles. I know you've measured the field of view in some vehicles that the cameras would augment that.
Yeah.
All right, so I see Professor Balling. I believe that you're out of Baltic states, Estonia, right? But I'm curious, what is your experience in terms of bringing our higher fidelity models and its requirements of high fidelity terrain input to the users? I mean, the addition to giving them good vehicles. So I'm sure this is Denmark, all right? I'm sure he's addressing, I'm guessing he's addressing NRMG, but I saw it where you said QGIS out there. So it looks like you are using some GIS systems but the high fidelity terrain input requirements may come down to LiDAR and some of these higher resolution issues.
Yeah.
Is that, you understand the question? Did I lose you, Bobby?
Oh, sorry. I thought that was for Professor Balling.
No, it's
yes.
I'm sorry. I'm reading out of the chat. He has asked a question directed to you.
Oh, I see. Okay, got it. No worries. Yeah, it's a great question. What level of fidelity of data is necessary? And I think that's the ultimate question, right? And the thrusts right now, we have some folks out here from ERDIC that are working that exact problem. And I would say, in my opinion, we have to be conservative from an engineering standpoint. Most of the folks working this problem are engineers. So data is king, and data is always, we need more data for everything. The end user right now is using Google Earth, right? So, and that's working for them. So Google Earth is a viable tool for route planning for them. We need to be sure that we don't swing the pendulum too far the other way. These end users, they have a mission. Time is king. They have to be fast. They have to move quickly. So any tool we develop, yes, it needs to have good technical engineering fidelity, but the utility of it is dictated by a young Marine or a young soldier that has to move quickly, and time is king. So we have to trade engineering fidelity with terrain data for effectiveness in the field, it's got to happen in seconds. So I think that's an important balance to remind ourselves, because we can get anywhere from 30-meter publicly available data to satellite imagery, drone flyover, 1 centimeter data. But it's a great question, because the end state is it's got to be a tool for the end user, and we got to find that balance.
I understand. I think this has a lot. I'm going off on a tangent too with it, but maybe with UAV flyovers and Blue Force Tracker, there's some opportunities of integrating high resolution terrain and route mapping.
Yeah.
Have you
Yeah,
seen?
definitely.
Okay. Yeah. I see he's typing. He's got Varsha, do you have any questions?
I could probably ask a few. They're very generic questions, but just something I guess that would be nice to have. Is there anything, what would you consider to be like a key lesson that you've learned from all these historical evaluation that NATC has had that would probably still guide your testing philosophy today? So what would be one thing, if you could share something that you were like, oh yeah, that was incredibly wrong that we did that way, and then now it's just something that's become an automatic, like this is how you're gonna do it kind of situation?
That's a good one. I'd have to think about that one for a minute. Yeah, there's been so many epiphanies. I guess I'm trying to think of mistakes. What are some pains that I've experienced that I don't want to experience again? And
Yeah.
this is kind of a simple answer for a lot of the smart folks on the phone. There's so many tech fellows on this phone, but most of the pains that I've ever experienced in testing and mobility are the simple things. It's the basics, man. It's configuration management. It's making sure that you're understanding why the data is what it is in the field before you go back. I mean, it's the basics. Stick to the basics, because that is what test engineering is tough because of the simpleness of it. I just got to go run this double lane change, right? Seems simple enough, but there's so many variables, there's so many things going on, and the procedure is very, very basic. The devil's in the details, and understanding that you're looking at your configurations, you're tracking tire pressures, you're validating your base configuration constantly is king. And I can pretty much say every mistake I've ever made as a test engineer boiled down to missing the basics. And because you're an engineer, so you get target fixated. You want to focus on the data and immerse into it and just work the end state, but you're forgetting step 3 and you're worrying about step 20,
20.
So I guess that would be my number one, which is kind of a philosophical answer, but I try to be philosophical every once in a while.
I think it really helps, especially for young engineers when we're starting off. Yeah, I do agree.
Yeah, totally.
Yeah. Yep. And then if nobody else has a question, again, another, I guess, more of an open-ended question from my side. You've done a lot of tests for different, vehicles, all of that, all that experience that you have. What would be one thing that you want modelers, because I'm from the modeling community. And yeah, I think one of the things that you said was just like, oh yeah, sometimes you need answers that are quick, and that's something that I know I need to keep my mind on. But do you have anything else, any other recommendation for modelers, especially because sometimes when you're not in the field, you don't really see it that way. We have a different experience. So what would you share to the modeling community about your experience that you've had in the field?
Yes, that's an excellent question, and you honestly you alluded to it, the field, right? Like being typically modeling engineer, you're running the models, and oftentimes it's remote. You're running it from your lab and that environment, or even a lot of our modeling sim engineers work from home, and our lead modeling sim engineer is in Virginia. So the getting out and witnessing the tests, being in the vehicle, being in the mud, you guys are so knowledgeable and you know the inputs into the virtual environment better than the test engineers. So you know what to look for, and you'll be able to glean variables that the test engineers aren't necessarily going to think of. You know, they're going to focus on test control and all these things, but your inputs into your model, the only way to get that is you being there, not relying on the test engineers, because the test engineers have a different priority, right? Their focus and their headspace is on customers and different management, and it's just different, you know. So to tie it all together, you know, it's we've had to do that out here, you know. It's the push pull between the different matrixed entities as a company. You know, relying on the test engineers, talking to the modeling and sim engineers. The best way to do that is face to face in the dirt during the test. And you know, that oftentimes it gets missed. You know, it's again a basic tip and trick, but a critical one, I would say. So yeah.
So get your hands dirty. That would be
Exactly.
Go into the mud.
Yeah, exactly. Yep, I would say so for sure. Yeah.
Sounds good.
Well, thank you very much for your talk. It's been enjoyable. Do we have any closeout remarks, Varsha?
Well, I guess that's it. Yeah, the ISTVS conference. Do you want to do that, Bobby? Do you want to say anything about it? You guys are one of our, well, you guys are the highest sponsor for our event, so.
Yeah, absolutely. So unfortunately, I don't get to go. My dad will be there in full force, but it's a great event, and looking forward to it. I know the focus this year is autonomy focused and mobility predictions. So I think there's last I heard, there's about 120, 130 people registered, and a lot going on. Very exciting. Dr. Sally Shoup is here actually right now on site, doing some planning for it. So hope to see you all there. And I know registration, I think, is closed, but you know, I'm sure if you want to go, just reach out to your POC within ISTVS, and there might be some options. But full steam ahead. And you know, I know there might be some questions related to government shutdown and all that, but honestly, a lot of the attendees are, you know, it's a mixed bag. So even if the government's shut down and they can't come, we'll probably still be north of 70 people up there. So plan is still to proceed. So appreciate you guys and ISTVS holding these conferences. Again, they're so critical. Wish I could be there. But yeah, looking forward to anybody that's going to enjoy the event. Varsha, anything you want to add to that one?
No, that's it. If you guys missed the registration, just reach out to Mike Parker, who's the chair of the conference, and we'll get you registered.
We got a student competition next year at the same time, but in University of Pretoria, and you don't have to be there to compete. So the details will be discussed at this conference, and the rules and everything will be generated out in February. So if you've got there's university professors. I know we got about 24, 25 people online. So if you got university professors out there, just toss it up to your students. And we may have Australia. We will have, of course, South Africa, Virginia, Mississippi State, and possibly University of Iowa right now signed up for the competition. We've still got plenty of time. Well, she's got slides on it.
I was just working on those slides, so I just pulled it up. but yeah, we have a student competition that we will be sharing more information about during the conference. So, yep.
Thank you, everybody, for attending.
Yep. Thank you, everybody.